Hi guys, how are you? Well, I wasn't thinking to do a demonstration today because I thought I couldn't do any demonstration for this week lesson. But then I watched this press conference some days ago. Have a look.
And I say, I've seen things when Tony mentions thermometers. They aim something at your forehead. They stay this far away, boom, and they tell you what your temperature is. I said, I've never seen that before. I've learned a lot. It's incredible. Go ahead, the back corner.
Okay, guys. So Missy is not happy to listen that to hear that voice. So well, you're very lucky because well, Trump had to be over his 70 years, had to be the president of the United States, and had to be under a pandemic crisis to learn what you're gonna learn this week. Okay, and compared with him, you actually is gonna learn it. I remember then that I have one of that devices he's talking about, a thermometer, that it doesn't have to have uh, a contact with your body to measure your body. For example, the best do, the best way to do it is to do it in your ear. I press the button and then I have my temperature. Don't worry about me. I'm 36.8 Celsius degrees. So it's the same concept as the device Trump was talking about, although of course those devices they use are more complex. You can measure the temperature from longer distances than this little and cheap device can do. Okay, so how can that happen? How can this device can measure temperature without having any contact with the body? Well, I'm sure you're already thinking about how, because you already studied about electromagnetic waves. If you don't have contact with something and you have information, most of the time is because electromagnetic waves. So yeah, this device actually can measure the electromagnetic waves that my body emit, that my body uh, emit in form of electromagnetic radiation. So yeah, you already know that objects reflect light. In our ways, reflect electromagnetic waves. That's why my face has colors. But objects also emit electromagnetic waves. Okay, we can't. Most of the time, we can't see that because it's in another part of the electromagnetic spectrum. But we can feel it because temperature is actually that. The different temperatures we can feel in objects, it's because they are emitting different electromagnetic radiation. So actually, temperature emits radiation of electromagnetic waves that are in the infrared spectrum. So this device here, we can see infrared waves, but this device can't do it. That's why it can measure temperature. Okay, so look, I'm in my kitchen now. It's a little dirty because, of course, we are cooking a lot in these days. So I have the stoves here. It's electric stove. This device here, it's very sensible. It's very limited. It can measure temperatures just between 34 and 44 Celsius degrees. So of course, if I try to measure this stove, it gives me an L that it says is too low. Temperature in the room is 23 Celsius degrees. I don't know where I have my thermometer, but yeah, it's more or less 23 Celsius degrees. That's why it can't measure that emission. Okay, but let's turn on a little until we had temperature that is higher than 20 degrees, and that can be written by this. Okay, just there. Let's see. Great. Now we have 36 Celsius degrees. It's not 23 anymore, it's 36. In other words, now emitting more radiation than before, than when it was 23 Celsius degrees. Okay, so let's have a look what happens if we leave it. So look what's happening now. We can see something. It's not like the other one. Now it's red. It's a lot more hot. I can't even touch it. It's dangerous, but now we can see. In other words, we can see the radiation now. So what happened? Before, in the difference between 23 and 36, we couldn't see the difference. But of course, the device could. So let's have a look on what happened there. Okay. Well, we were saying that all the objects also emit electromagnetic waves. That's what is called electromagnetic radiation. So objects just not just they don't just reflect electromagnetic waves, but also emit. Okay, why? Because well, objects are made of atoms, and the atoms are vibrating, so they work as little uh, antennas. Okay, and as we increase the temperature, this vibration is going to increase too, so it's going to change the radiation. Okay, so that's how it happens. Of course, we can't see this radiation because these radiations are more in the infrared spectrum, not in the visible light spectrum. But sometimes they get into the visible spectrum, and that's we're gonna talk a little about that now. Okay, so the objects that emit radiation, of course, the objects have different spectrums on depending on which kind of electromagnetic waves they emit and in what intensity. So you can see, for example, here the daylight. Of course, the daylight it's like saying the sun, but just in the visible spectrum. It has this spectrum. Okay, the sun, of course, emits a lot more than that. Also in the infrared and also in the other shorter wavelengths. The fluorescent objects, what color they have? Green. That's why here, as you can see, it's a very strange spectrum. And the incandescent objects are normally in the red area. So let's see the electromagnetic spectrum of the stoves we were playing with. So let's imagine that, well, here is wavelength and intensity. Let's imagine that here between red and blue are the wavelengths from the electromagnetic visible spectrum. Okay, little like this picture here. Okay, so when the stove was cold, like room temperature, that it was 22 degrees, the spectrum was a little like that. Okay, more or less. It has a peak, and it's mostly in the infrared or even higher spectrum. Okay, so we could see uh, just the light that the stove was reflecting. Okay, not the waves that it was emitting. Okay, when I put it little hot to 36, where this machine could read that infrared electromagnetic waves, something like this happened. The spectrum moved a little to the left and the peak increased. Okay, so this is 36 Celsius degrees, let's say. Okay, and this other one it was 23 Celsius degrees room temperature. But look, in 36 Celsius degrees, the stove was the peak was still in the infrared spectrum. But what happened when we heat it up more, a lot more? Well, that spectrum moved here. The peak was even higher, and it was already inside the visible light spectrum. I remember it was a kind of first red, then it went a little orange. So that's because, well, first it had this peak in the area of the red color in the visible spectrum. But what happened then? It went even more higher and it get into the orange area of wavelengths in the visible light spectrum. That's why as you heat it up something, first it's red, then it starts to turn orange, then yellow, and there's flames that has blue color. It's because they are very hot. And well, the radiation that objects emit, the electromagnetic radiation, it's called thermal radiation. And as I was telling you there, if you heat up something, first we can't see nothing because that radiation is still in the infrared, but then as you can see here, we can start to see first red, and every time it's more yellow. Okay, so that luminosity, or that it can that it at the end of the day is it's power, which can be translated to intensity. It follows this law, Stefan Boltzmann law, and as you can see, it depends a lot on the temperature. Temperature is to the far. Okay, so it depends a lot on the temperature, as we saw. And well, there's a law that can relate the intensity with the highest peak that we can have in these spectrums. So you can see here, let me make this bigger. Here's the thermal radiation of some object. So you see here, when it's not too hot, the peak is very little, not too high, and it's in the infrared spectrum. When it's a little more hot, it gets into the visual light spectrum, okay, until it goes even to the blue colors, as I was saying. So this equation here, with this equation, we can know which wavelength, at which temperature we're gonna have the highest wavelength. Okay, we can use that. Let's see, for example, this little machine here, what it does at the end of the day then is to measure that peak, the value of that uh, peak of wavelength. So at the end, what it captures is that wavelength. Okay, so let's see what in my body at that temperature that I measured with this, what's that peak of what wavelength is that peak. Okay, so I have it here. That's the equation, but of course I solved the wavelength, and this is my temperature that it was 36.8 Celsius, but here it's in Kelvin units. Okay, the absolute temperature. So let's have a look. I have the calculator here. That 289 and So it's like 9,354 nanometers. I'm putting the units I'm using nanometers to see that it's very to compare with the visible light spectrum. Remember that visible light spectrum is until around uh, 500, say 750. Okay, then it's infrared, so it's a lot higher. So that's the peak of the radiation I'm having with that temperature. And that's it about the thermal radiation. Let me know if you have questions. Okay, bye.